So today the topic is discrete signal processing on graphs, especially on graph signal processing. And here's the acknowledgements. And the first charming lady is my advisor, Professor Gillian Wachevich. And now he's the department head of electrical and computer engineering. And also he's the joint professor in biomedical engineering. The second one is Dr. Alexei Taylor, and he's an ex-PhD student of my advisor. And now I'm working with him on this special topic of discrete signal processing on graphs. And the third professor, Professor Jose Moro, and he also worked on this project. And these two professors, they are from civil engineering, and we work on a bridge project that I will show you. And this old man called Professor Michael Bila, and this is the dean of our engineering school, Dean James Taylor. And here's our group. Our group leader is my advisor, and each of us should choose the academy. And mine is Adam. So here's our line today. So first I will introduce the motivation, why we are interested in this topic. Then go to the theoretical framework of discrete signal processing graphs. Then a specific task called signal processing in inpainting. And then we'll talk about some visual work. So let's start with the motivation. And I'll motivate from two perspectives. First application, another side is theoretical side. So first application. When people talk about graphs, they usually show low-free main aspects, the internet, bioinformatics, and some friendships. They're all very broad topics. Now I just want to zoom into a very specific topic and motivate from a very tiny example. The temperature. So here is the temperatures measured from 150 weather stations across the United States. So the color shows the temperature value from 12 Fahrenheit to 71 Fahrenheit. For example, the hottest part will be the Miami is 71 Fahrenheit. And we can think about those temperatures. There are some geodetic properties behind those values. For example, if we want to represent the temperature in New York, we can assume it's close to the temperature in New York or in Philadelphia, because they're close in geodetic distance. So when we get those signals, or this data, we can assume there's some defects and irregular structure behind this data. And we are interested to analyze and process those data. It's very different from like time series or images. It has a very regular structured data behind it. But here we don't have that kind of structure. So we need some new techniques to process it. So when people do graphs, some people do network structure. It means they analyze the structure itself. For example, they do community detection. They do various importance. They do shortest paths and graphs. They analyze the structure itself. But what we want to do is different. We want to process information on graphs. We want to do some classification or detection for the signal on the graph. It's like those examples. We have the structure, and we also have the signal on the structure. And from the theoretical side, let's recap the Classical Dsp. So in Classical Dsp, we often look at those two kinds of signals, time series or digital images. And this is the structure behind it. For example, at each time step, we take one step and move forward. All nodes or all time step here is identical from the structure. Also in this digital image. So if we ignore the boundary condition, each pixel connects to the four neighborhoods, and all pixels are identical from the structure. And we do a lot of work on those structures. We do Fourier transform, we do wavelets, we do directional wavelets. We have frame, we have sparse rotation. And we try to ask, if we go to the limit, and can we do better? And what kind of other things we can do? And one way we can think about is generalize the framework. We can generalize the signal you process. So if we want to generalize the signal, now let's go back to see what signal we are interested in previously. So in classical DSP, so here I just zoom into the finite time series. It's finite and discrete. So the thing about the signal is a map from the time step, punch the red dot from time step to a series of contact values. So in other words, it's for each time step there are some contact value associated with that. And if we ignore all the values and just look at those time steps, we can abstract them. So we ignore the concept of time. We just think about it some vertices or some nodes. This is the structure behind the signal. And we call it shift. So shift or delay means one move from this node to this node. So that's for classical DSP. So if we want to generalize it, and we assume this is the most elementary operator. So in 2006, Professor Pushu and Mora, they tried to generalize the framework. And they created something called algebraic signal processing. So in algebraic signal processing, we extend the concept of shift. So for example, here is for 1D time series, the shift is from time n to n plus 1. And also for space, for time you cannot go back, you can just go to the future. But for space you can go backward and forward. And also one generalization is called neighborhood shift. You can go back, you can go to the future, and you can stay in yourself with different weights. But here, still the problem is all the nodes have the same structure, have the same identical structure. So if I replace this by n minus 1, so here's t n minus 1 to tn. So all the nodes are identical. So can we extend the framework even more? So here in 2013, Dr. Sandra Taylor and Professor Mora, they created a new framework called DSP on graphs. So they extend the shift more to be a graph shift. So here is a very tiny example for graphs. So here this node has 3 neighbors, but this node has 4 neighbors. So then this graph is not identical. So it has more compact structure. You can represent more complex structure. And the signal, the graph signal defined on those framework is, so for each node there is some value associated with that. And notice that the structure behind those verses are different and they are more complex. So one thing to notice is DSP on graphs is not graph theory. So graph theory consider a problem and analyze the graph structure itself, but we consider the information on the structure. So we are doing signal processing. We are doing the signal on the structure. So it's different. And also it's not probabilistic graphical model. So in probabilistic graphical model, they consider the structure of a series of random variables. So for example, am I smart? Am I cute? Do the audience like me? And we assume smart and cute are independent. But if we observe if the audience like me, then they are dependent. So they have a B structure here. And in probabilistic graphic model, each node represents one random variable, and there is some probabilistic distribution associated with that. Then you can build a generative model and do some inference or learning on that. But we are talking about something like the internet, some more network than graph. So another view is, so if you get a data matrix, So the row is object, column features. So DSP on graphs consider each node is one object, and in probabilistic graphical model, each node is one feature. So we view things from the row instead of the probabilistic graphical model view things from feature. So there are lots of confliction of the concepts on network and graphs. So actually, if you view things from feature, it should call graph. If you view things from node, from object, it should call network. But there's too much confliction there, so now people just pick words randomly. So here, actually, the name should be discrete signal processing on networks, but like graphs may be more fancy name. So we see that we have some application. Like we want to process this information or the data on the network, and we also want to generalize the framework of classical Dsp. Then it's heavy handed. We have a theory that can process the information on networks. So we want to combine the idea and achieve something. So then I was talking more about the framework of DSP on graphs, and I will give you more intuition. So still we go back to the classical DSP, and this is the structure behind we often consider time series and digital images. But nowadays we have more complex data, like the sensor network, also the logs or the web pages. There are lots of information on those structure, and we want to process it. So we need these new techniques. And I'll compare the two frameworks, the classical DSP and DSP on graphs, via some key concepts: signal, shift, filtering, Fourier transform, and total variation. I think those concepts are very... So you guys should be very familiar with those concepts. And you will see that in the framework of classical, in the framework of DSP on graphs, it's a natural generalization. So it should not be very hard for you to understand. And when we think about some finite time series, this is what we will think about. For each time step, there is some value associated with that. And for a signal, it's, if you ignore the concept of time, then it's a map from the verses to a series of complex values. In other words, for each verse, there's a value associated with that. And for graph signal, still it's a map from verses to complex values, but there are more complex structure, irregular structure behind it. And you can think about each node is CD, and the value associated with that is the temperature. And CD connected each other by the geodetic distance. So one key concept like I mentioned previously, in classical Dsp is called shift. It's nothing but the delay, like from current time to the future. And we can represent in a signal permutation matrix. So here I use 3 nodes as a sample. So here I get a 3 by 3 matrix. It's nothing but one shift from the diagonal. So from 1 you shift to 2, from 2 shift to 1, and 3 go back to 1. And in DSP on graphs, we can be a little bit more general. And we can add more edges. So for example here, we can add one more edge from 2 to 1. Then the structure is not identical. So for example here, if you put this guy to this one, so it's a loop, so it's all identical. It's all the same. But here, this guy is different from all the others because it's one more edge. And then we can use we still use this very similar matrix to represent that, but we get one here. And we can be even more general. We can have a self loop and edge weight other than 1 and 0. It can be other values. So here the structure here is not the time connection. Again, it's some very abstract concept. You can think it as a relational dependencies between each pair of nodes. And let's assume each node is one person. So then there's some connection between the first one and the second one. So maybe this guy like this one. And the second guy really likes the first one, but like him very much, like himself very much. And the third guy hate the first one. So just by the structure, maybe we can predict they have different personalities. So filtering. For linear shift invariant system, we assume that the filtering is the operator H worked on the signal. And because it's finite time series, so we should consider the boundary condition. So the mode here. And I think this formula is very familiar to you. But we can form it in a different way. We can represent it in a matrix form. So here is Y matrix, and this is H, and this is X. And because it's a convolution, so the matrix is a cyclic matrix. I can represent the polynomial of a cyclic permutation matrix. So here is one shift from the diagram. It's the C cyclic permutation matrix, and it's a polynomial of that matrix and work on X. In other words, so we replace this by C, and this is X, which input signal, and get output signal Y. So it's some polynomial of the cyclic permutation matrix. I like this form better because it's more clear. It's just some polynomial of cyclic permutation matrix work on X. And we can naturally generalize this. I replace C by A. So previously we see that we add some more edges at this edge and this edge, then we get A. If we specify this A is a cyclic permutation matrix, then we go back to classical Dsp. Then it's a normal filter. But since this graph shift we plug in here is more compact, so we call it graph filter. But it's still a natural generalization because it still follows it's a polynomial of graph shift. So Fourier transform. Fourier transform is if we do the eigen decomposition of the cyclic permutation matrix. Their eigenvectors are forms the DFT matrix. So this is the DFT matrix, this is the new signal, and this is the signal in the spectral domain. And you can do inverse and go back to the signal. And we do the similar thing. We do the eigen decomposition for A, and the generalized eigenvalues, the eigenvectors here, and we call that a graph Fourier transform. But to notice here, this C has a very nice property. It's one shift from the diagram. But here, this A can be anything. You can plug in any structure. So it can be sometimes undiagonalizable. So we use the Jordan decomposition. It means we can still decompose it, but this J may not be a diagonal matrix. There's some one off the diagram. But still we can still decompose it. And we define a new called F hat for this form. We can decompose it in this way, and we can get the graph Fourier transform in this signal in the Fourier domain and do the inverse Fourier transform and get back the signal. So previously, this F here is an orthogonal matrix. So F transpose F is identity matrix. But here F and F tilde is not a orthogonal matrix. It's called biorthogonal. It's a biorthogonal pair of bases. So the last concept is called total variation. So I introduced this concept because later when I do graphical inpainting, I will use this concept. It represents the smoothness of the signal. So when we try to describe the smoothness of a finite time sequence, we have this total variation. And it's defined by the sum of the difference between two sective samples. So at time n, we compare the difference between this one and the previous one, and take the magnitude and sum it. And because it's finite time series, so I have mode n to take care of the boundary condition. In other words, I can represent in vector matrix form. So this is original signal minus the shift version. X is the delay version. So that's the L1 difference between the current version and the shift version. And we can do the similar thing for graph signal. It just has more complex structure, but we can still take care of that by the graph shift here. So this now is the difference between this n sample n and the weighted version. So this capital N is these neighborhoods of n. So I weight all the neighbor for n and find their difference and sum it. So still I can represent in vector matrix form. Still Ax is a shift version, but this shift is more complex. We can still specify this A to be the cyclic permutation matrix, C. And then you will find, you go back to the previous definition. And notice here, this A, we should normalize its largest eigenvalue to be 1. So, yeah, so now we have the total variation. And we want to be more general. It's just, so this guy describes the smoothness of a signal. And we can have more dimension more norms to describe the smoothness. For example, we have P form. And we see that total variation is just specifying this P to be 1. So if you plug in this P to be 1, then the constant is 1, and here's 1, then you go back to L1 norm. And we can get a quadratic form by specifying P to be 2. So this is half here, and we get a quadratic form here. It's a very nice quadratic form. And in this talk, I ignore the constant half and just focus on this quadratic form. Still, those graph shifts has their largest eigenvalue to be 1 because I normalize it. And you can think about the cyclic permutation matrix here. It has the largest eigenvalue to be 1. So a recap for the theoretical framework, I compare classical Dsp with Dsp on graphs. You see that it's the same concepts, but it's just natural generalization. It's generalized by the key concept called graph shift. It represents more complex and irregular structure. So then I go back to a specific task called graph signal painting. And so first thing is, what is graph signal painting? So still we go back to the temperature example. So we measure 150 temperatures from different cities across the United States. And for example, in Pittsburgh, we missed that for some reason we don't have the value for temperature. And we want to use some techniques to recover the value. And we actually do the similar thing for image printing. For example, we call image, and there are some cracks here. And we want to use some techniques to recover the part that we're missing and get the original image. The image, we have a very regular structure. It's a grid structure. We have a lattice. Each node connect to the 4 neighborhoods. But for temperature, we don't have that kind of regular structure. But still we can build a graph structure by building the graph shift to represent the structure, represent the geodesic distance and relationship. And the process of reconstructing the lost or so-called corrupted temperature data is called temperature painting. So for graph signal painting is the process of reconstructing the corrupted parts of signals with underlying complex and irregular structures. So why it's useful? You can handle signals with complex and irregular structure, and it has application in regression and classification. So again, the task is given a corrupted signal with a complex structure and want to inpaint or recover the lost part. So here's formulation. This T is our measurement. So we measure T, but it's a corrupted signal. So there are some values are missing. The black dots shows this missing part, and red dots shows the measured part. So we can split the two parts by in this M and U. So M measures is the uncorrupted indices or measured part. U is the unmeasured part. So we have the data on the measured part. And for U, we have it's plotted on those black dots. X is a true graph signal we want to recover. So X is hidden. We want to recover X. And W is some noise. The task is given Tn, measured part of the measured signal. We want to recover X. That's the task. So previously, when people do image painting, they use a technique called total variation minimization. So they assume, so when you zoom into a small part of the image and look at it, I'm not sure if you can look carefully. So this image is pretty smooth with some edges. So the idea is, if you zoom into a small part, each part is smooth. So we punish the unsmoothness. To describe the smoothness of image, we have the concept called total variation. I introduced the total variation of finite time series previously, and here's for 2D images. And here is because 2D image is 2-dimensional. So then you have, remember you have a lattice structure for the graph, and we zoom to the pixel values. And here we have two directions. This is for horizontal, and the second one is for vertical. So the part here is the L2 norm of the gradient. And so the total variation of the 2D images is the sum of the magnitude of the L2 distance. So still the signal model is we have a measurement. This is T is a measured image with cracks, and X is the original image we want to recover. And W is some noise, and in the unmeasured parts, the noise are very big, and we cannot use that information. So we just use Tn to recover X. Remember, T and X are just images. And we form an optimization problem like to minimize the total variation of the X subject to, so the estimate plus noise is your measurements. And on the measured parts, the noise are pretty small. It's bounded by something. That's the how people do the imaging painting. But so people spend 10 years to solve this problem because it's L2 then L1 It's you can always find the faster algorithm to solve this problem. But in general, this is a very general formulation to do the imaging painting. And for graphical painting, we can do the similar thing. And still the problem is, given a structure, we want to recover the measurements. So the example is still the temperature. So we want to recover the missing value in Pittsburgh. So there's a temperature, and we have Philadelphia and Cleveland. They're very close to Pittsburgh, and we want to recover the value in Pittsburgh. So still we will use the total variation and smoothness. Again, this is a signal model, but T and X here are not signal again, they're graphical, which means there are some complex and irregular structure behind them. Still we want to use Tm to recover X, and form this almost the same way. So S2 here represents the quadratic form of the total variation, and defined by, in this way, measure the smoothness of the signal, and we have the same restricts here. But here are three things to notice. First, we plug in A here. This A represents the complex and irregular structure. It handles that. And in previous imaging painting, is a cyclic implementation matrix. It represents the structure of the lattice structure. But here we have more complex structure. And second thing is, previously they used the L1 node. You use L1 node because in images you want to separate edges and background. The lots of background, they are very smooth, and there are some sharp edges. L1 node promote the sparsity. You want to test the edge without take care of the smooth background. But here we don't have a very clear concept for edges on the graph signal. So you want each node to have a small variance. So you use the quadratic form, you use the L2 node. Then the good thing is here in objective function, it's a quadratic form. It means it's very easy to solve. It's a strongly convex problem. So we form in two different ways. If the noise level is very small, so this epsilon is 0, then we call it hard constraint, and call graph toleration minimization. So this epsilon is 0, and we can put this, so it means like T, this Tm, so because this guy is 0, so T, Xm, Tm, so we can only have this constraint. And we focus on minimizing the quadratic form of the total variation of X. And we can actually solve in a closed form solution. And we represent the quadratic form in this way. This A tilde is quadratic form. And you can separate it by the measured part and unmeasured part. So here we get 2 by 2 blocks. And you split that and you get 4 terms here. And we know that by the constraint Tm equals to Xm. So you replace here is known value, and you take the gradient for Xu, the unknown part. You set the derivative to 0, and you get a closed solution. Its sum operator works on the Tm. It's a linear operator. Another one is you can do some soft constraint. It means this epsilon is not 0. And we put the constraint into the object function. So we put this constraint into the object function, and we can show that if you choose the epsilon well and this lambda well, then those two products are equivalent. You can prove that. And so here we want Xm to be close to Tm, and still we want to push this X, our estimate, to be smooth. Because I add the regularization here, so I call it graph total variation regularization. And still for this problem, I can get a closed form solution. So this comparison, we solve in the soft version and hard version. for the regularization, still we set the derivative to 0 and do some algebra, then we get close solution here. And still is some operator works on Tn. And here you can see, like you can find, if you set lambda to be 0, then you don't punish the smoothness. Then x is nothing but Tn. But if you put this lambda to be very large, then the result is very, very smooth on the graph. So then we want to answer like how well we can do by using this algorithm. So we try to bound the estimate error. So we assume x0 is the true graph signal that we want to recover, and x hat is the optimum from the object function, from the optimization problem. And Z0 is estimation error is defined by the difference between the true graph signal and the optimal solution. And let's assume the smoothness is n squared, and the difference between the measurements and the true graph signal on the measured part is bounded by something. And also the P and Q are the spectral norm of some matrices. Then we can get this theorem. So on the unmeasured part, on the corrected parts, the difference between the true graph signal and our estimate is bounded by this guy. And let's look at this a little bit. So this epsilon is the upper bound of, on the measured part, the true graph signal, the true graph signal, and the measurement. So here it means if we measure it pretty well, then this guy is 0, so we get a lower bound. So it means we want to measure our true graph signal well. The second thing is the smoothness of the true graph signal. So still, if the graph signal is very, very smooth, so n is small, then we have a lower bound. And this matrix, very interesting, is identity matrix plus the graph shift, and we can split them in two blocks by separating by the correct indices and uncorrect indices. You see that P is the spectral norm of this part, and Q is the spectral norm of this part. And usually this guy is pretty small, so we ignore this P and only focus on Q. If we won't get a lower bound, then it means we won't have a smaller spectral norm of this matrix. Which means if you have more measurements of n, so this part will be bigger, and this part will shrink. You'll get a smaller Q. So basically, if we want to get a lower bound, we want to get a smaller estimation error. We want the true graph signal to be measured correctly. We want the true graph signal to be smooth, and also we want more measurements. So recap for this section, we set up this optimization problem, and we have two kind of version, hard version and soft version, and we bound the estimation error. So here's some experimental results. So the first example is online block classification. So we have more than one dominant related blocks. So we label them as +1, -1. And so for example, for this graph, each node is one block. And you see some value associated with +1 or -1. They represent different parties. And the idea is, so we hide some values here. Assume we don't know those values. And we want to use the previous techniques to recover those values and see if we can predict which party this block belongs to. And we evaluate that by accuracy. So here is some method that we are trying to compare. The first one called harmonic function. So it's pretty similar to graphical variation minimization. This is constraint is Tm equals to Xn is the same, but they have a different object function. It's some way to measure the smoothness. So it measures the difference between the two adjacent values here, and also weighted by their edge weight. So this method published in 2003, and last year it won the 10-year Best Paper Award for International Conference on Machine Learning. So this it's pretty easy, but it's definitely not a trivial method. And this guy, adaptive graph theory, I proposed this method last year. It's a semi-supervised classifier, like combine decisions from multiple graph filters, and you train this filter coefficients. So this is the filter, and you train this coefficients in a semi-supervised way, and then we put this, operate on the input signal, and get some output, and do the classification. So we compare those four methods: minimization, regression approach that I introduced previously, and also compare them with the harmonic function and adaptive graph theory. So here's the result. So x-axis are labeling ratio. It means the percentage of the label blocks. And y-axis is accuracy. It means higher means better. So here is 5 out of 1,000, which means I only label 6 blocks. When I only label 6 blocks, harmonic function works like by chance is 50%. And the best algorithm is adaptive graph theory and achieve like 85% accuracy. And only by labeling 12 blocks, there are more than 1,000 blocks, and I only label 12 blocks and try to recover others. And the minimization approach achieve almost 95% accuracy. And it seems to converge here. You see that when I label 100 blocks, then the harmonic function eventually catch up with the method I proposed. So another task is called bridge condition identification. This is a very interesting project. And the idea is we put on sensors. So we want to measure the bridge condition. So we build a bridge and we want to know if the bridge will help or not. It may fail. We want to prevent that, so we put some sensors on the bridge and do some analysis for the signal and try to predict if this bridge has some cracks at this part, then we want to send a team to fix them. So here the idea is we don't put sensors on the bridge, we put sensors on the vehicle, and we analyze the signal from the vehicle and do some analysis and report the error. So in lab scale, in the lab, we build a lab scale bridge, and we'll mimic the cracks. So we put some weights, and for each structure, we analyze the signal and try to predict so this is our input. We sense this acceleration signal, and we want to predict what kind of bridge structure that we measure from. So then we build a graph. Each node represents the acceleration signal, and the value associated with that is how many graphs we put, how much weight we put on this structure. So we're still doing painting, but now this task is not classification, it's regression. So we measure by mean square error, and we compare both three methods because that graph figuring is a classified, not regression model. So still, x-axis is the labeling ratio, y-axis is the mean square error. So here, lower means better because y-axis is error. So we almost find the similar thing the harmonic functions fail on this task. So a little bit about future work. So like what I said, there are two things we want to focus. One is theoretical framework. Another part is some specific tasks. So there are lots of things to do in both in network, but from theoretical framework we want to do multi-resolution analysis. We want to do frame representation. We also want to do graph dictionary. In special tasks we want to do generic signal recovery. We want to do shift learning, fast Fourier transform, and also some application to the distributed consensus. And now there are also some people do signal processing on graphs. The SU work, they put their very powerful framework on images. The idea for us is not work on images, we want to do signal analysis for real networks. So here are three take-home messages. The first thing is DSP on graphs is a promising and emergency theoretical framework that generalizes classical Dsp via the very basic concept called shift. And second thing is the graph signal painting via total variation minimization. It's a pretty simple but powerful semi-supervised model that if you invent some classifier and you want to find something to compare, you can choose that. And the third thing is there are lots of work to do. So I introduce you guys to join us and fill the gaps. Thank you very much.